All right, guys, so let's go ahead and get started. Last time in class, we learned about electrons and how whenever they jump from one energy level to another energy level, that they give off different colors of light, and how every element gives off a different color because every element has a different number of electrons. And we also talked about how light kind of travels like a wave and it acts a little bit like a particle, which we call a photon. And so what we're going to talk about today is more on electrons and exactly how they fill in the different energy levels around the atom. Okay, so there's a very specific way that the electrons are located around the atom. Okay, and we call that the quantum theory of the atom. So I'm going to go ahead and share my screen so you guys can see the PowerPoint. And the PowerPoint is posted in your modules, so you don't have to worry about writing down any of these notes. Okay, so in 1913, Niels Bohr came up with this planetary model of the atom. And it's the one that we're used to seeing, where the electrons just kind of circle around and orbit the nucleus. Okay, and so that's why they call it a planetary model, because it looks like the sun in the middle with the planets just going around in a circle. This model is now outdated. We know that electrons kind of fill in more of a three-dimensional space around the nucleus, not really just stuck on this little ring, jumping from energy level to energy level. But this was the initial model that was created by Niels Bohr. It started to be updated to the quantum mechanical model with Heisenberg. Heisenberg came up with an uncertainty principle. He said that you can never really know exactly where an electron is located and how fast it's going at the same time, because as soon as you pinpoint where it's at, it's already moving to another spot, okay? Because electrons are constantly moving around. And so the main idea here is that we can only know an estimation or a probability of where that electron is going to be located at any given time. And so another guy named Schrödinger, he treated electrons like waves, okay? And he came up with a model called the quantum mechanical model of the atom. And so what he did is he designed and predicted this three-dimensional region where the electrons might be located. And he called those the atomic orbitals. Here's a picture of what the different atomic orbitals look like. So if an electron is in the first energy level, it's going to be floating around the nucleus in the shape of a sphere, okay, anywhere in this three-dimensional sphere region. If it is in a second energy level, like a higher energy level, it can be floating around in the shape of a dumbbell, okay? So this kind of looks like a little infinity sign, and we call it a dumbbell shape. If it's in the next energy level, then it's in the shape of a clover. And if you can tell, it's kind of like a four-leaf clover. And so in the D energy level, you have 5 different ways that the electrons could be floating around the nucleus. Okay, and then we jump up to the next level, which is the F level, and there's 7 different ways that it can be around the nucleus. And we don't really have a name for this shape. We just say it's too complex because, I mean, look at it. It just looks kind of like a flower or something. So we have a sphere, a dumbbell, clover, and then complex. And this is for the S level, the P level, the D level, and the F level. There are also principal quantum numbers, and I don't want to get into too much detail because this gets really deep. But all you need to know is that there's 4 different energy levels, and in each energy level, there are sublevels. So on level 1, there's only 1 sublevel. On level 2, there's actually 2 sublevels. In level 3, there's 3, and in level 4, there's 4. Okay, and so those are all the different energy levels that electrons could be in when they're around the nucleus in an atom. All right, so this is starting the principles of how we're going to do our assignment today for electron configuration. Electron configuration is the way that the elements, the electrons are arranged around the atom of a certain element. And so the first rule is the off-ball principle. Okay, off-ball came up with the idea that each electron is going to occupy a low energy level and then a higher one, and then a higher one once the lower energy levels are full. It's kind of like on a video game. You have to pass level 1 before you get to level 2. And you have to pass level 2 before you get to level 3. So you're not going to find an electron way up here in this energy level if all of it below it is empty. Okay, so they're going to fill in from lower energy levels and build their way up. Another principle is the Pauli exclusion principle. He states that a maximum of 2 electrons can be in each orbital. Okay, so you can't have more than 2. Once it has 2, it's full. Those electrons have to have opposite spins. Okay, and what I mean by opposite spins is that electrons are both negative. We always say positive and negatives attract. But if you have 2 negatives, have you ever tried to get a magnet and push it together on the ends that don't go together? You can feel kind of like that push back, you know, it doesn't want to go. That's because you're trying to push 2 negatives together. And so that's how electrons are. They're 2 negatives, right? And they don't want to be close to each other. So they're going to have opposite spins, so that way they're constantly spinning around the nucleus in opposite directions from each other to stay far apart, okay, because they're both negatives. And then we have Hund's rule. Hund's rule states that the electrons are going to spread out as much as possible until the sublevel gets full, and then they're going to go back and squeeze in where they need to. Okay, they're not going to just squish in right next to each other. They're going to take up as much space as possible. And so I have kind of a dumb story to tell you, but hopefully it'll help you remember Hund's rule. Last football season, at the beginning of the season, I was sitting in the spot that I always sit in for the football games. It's like the second seat on the second row, right in the middle. And I'm always there because I'm there with student council. Well, this little girl and her boyfriend walk up, and she's complaining to him that I'm in her seat. And I'm like, girl, I sit here every single year for 10 years in this seat, and I have my ticket to prove it. Well, the whole row is empty. Okay, it's not like it's a packed out game, and the whole bleacher is empty. And she comes and she literally sits right next to me to where her hip is touching my hip on the side. And I'm like, excuse you? Like, we had a little throwdown. But I was just like, you don't do that to people. You know what I mean? Like, even if I was in her seat, you know, she could have said like, excuse me, you're in my seat. Can you please scoot over? Or, you know, just space down a little bit, because nobody was there in the whole row. But no, she came and sat right next to me. And so we had an issue. But that is just something that typically you don't do, right? If there's space, you're going to kind of spread out and take your space. It's kind of like being on an elevator. It would be real weird if you were the only person standing in an elevator, and then, you know, you reach a floor and the doors open and somebody wants to come in. It'd be real weird if they came and like stood right next to you, right? Like typically in an elevator, you kind of spread out. One person goes on this side, the other person goes on the other side. Especially now with like our social distancing, we're all getting pretty good at spacing out from people. So that's kind of just like this general rule that we follow. So electrons follow that rule as well. They're not going to come in and sit right next to another electron if they don't have to, because they're both negatives, right? They want to take up as much space as possible. They don't want to be next to each other. So they're going to fill in the energy levels apart from each other before they have to come back in and squeeze next to another electron. Okay, so that's Hund's rule. This is a really great chart. Go back to this chart whenever you're going to take your test, okay, because it has all the information in one place. It has the name of the orbital, S, P, D, and F. It has the shape that that orbital makes, the sphere, the dumbbell, the clover, and the complex one. It has the number of maximum electrons that it can hold. An S shape only has one orientation around the nucleus because it's a sphere, right? No matter which way you turn a sphere, that's only one possible orientation. It's going to be the same on all sides. So in that one orientation, it can hold 2 electrons. So that's why the maximum is 2. With the dumbbell shape, I'm going to go back a second. There's 3 different ways that the dumbbell shape can be around the axis. It can be like this, it can be like this, or it could be like that, okay? And so each one of these shapes can hold 2 electrons, all right? So that's why in our chart, it says that it can hold 6, because you have 3 different orientations. So each one can hold 2 electrons. So you have a total number of 6 electrons that can fit in the P level. In the D level, there's 5 different orientations, which means that it can hold 10 electrons, 2 per orientation, right? 5 times 2. And then in the F level, there's 7 orientations times 2. That gives you 14 maximum electrons that can be held. Okay, that's where we're ending that. Okay, so what I want to do now is I want to show you guys some examples. You're going to need a sheet of paper, okay, so that you can kind of follow along and write down the examples. You'll also need a sheet of paper to do your assignment today, because what you're going to do is take a picture of your work and submit it that way. Okay. Okay, so this is a special electron configuration periodic table. And the only difference between this and a regular periodic table is that in the yellow boxes, it has the energy and the sublevels for where the electrons would go. So hydrogen is in the 1s energy level. It's on the lowest energy level. It's in the S shape, which is a sphere, and it's the first element in that level. So it only has 1 electron there, okay? Helium is also in the first energy level with an S shape. Lithium and beryllium are on the second energy level, the 2s level. And then over here in the 2p level, you have these 6 elements, okay? So in yellow, it tells you exactly what energy level those elements are taking up, okay? And we have 4 different blocks on the periodic table. So this is the S block. And if you look, all of these are S's. Over here is the P block, and all of these are P's. The D block, D levels, and down here, the F block, okay? And these are the F levels. And so we talked about the number of electrons that each one could hold. S can only hold 2. Well, if you look at the S block, there's only 2 elements there. Those are the electrons, okay? If you look at the P block, we said P can hold 6 electrons. 1, 2, 3, 4, 5, 6. D can hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And F can hold 14. So there's 14 going across here. Okay. So if the S level is filled up, it's going to have a 2. If the P level is filled up, it's going to have a 6. The D level is filled up with 10, and the F is filled up with 14. Okay. This periodic table is on your modules. It's also on the home page. If you click on resources, you can access it from the resources page. Okay, under buddies, I think I have it under buddies, and it has the electron configuration periodic table. Okay, so there's 2 places that you can access this. And if you're in class, you have it at your desk. Okay. I suggest if you do have a printer or any way to print it out that you can do that. You don't have to, but for me, it makes it easier to have it like in front of me where I can kind of like touch it, and I don't know. I'm just kind of like a more manipulative type person. Okay, so this is our electron configuration periodic table. So what we're going to do is we're going to go through and we're going to label each sublevel, okay, the energy levels and how many electrons can fit, okay? So we start at the beginning of the periodic table and you go straight across row by row until you end up on whatever element you want to be on, okay? So somebody give me a number between 1 and 50. 20? Okay, so we're going to do number 20. Okay, so you'll find number 20, which is calcium. And we're going to write the electron configuration all the way up until we get to calcium. Okay, so we start at the beginning and we're going to go row by row till we get there. So we're starting here and we're looking at what's in yellow and we're counting how many of them are in that level. So we're 1s and there's 2 of them. So 1s2. Next row, 2s2. Keep going. 2p6, 3s2, 3p6, 4s2, and that's where we're stopping. Okay, so that's your electron configuration for calcium. That is the order that the electrons are going to fill in the energy levels until they get there. Okay, let's look at another one. Any other number between 1 and 50. number 50. Okay. Sn, which is 10. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p2, because we're on the second one. So instead of saying 5p6, that would take us all the way over here, but we're on 5p2. Okay, so let's go ahead and write down some of these examples to help you guys out. So this is where you need a sheet of paper. Take some notes. Okay, so we're titling the notes Electron Configuration and Orbital Notation. Okay, so the first one that we're going to do is silicon, which is Si. And we're going to write the electron configuration first. And I'm just going to abbreviate that as EC. Okay, so we'll need our periodic table. We are trying to get to silicon, which is number 14. Start at the beginning and go row by row, writing down what's in yellow and counting how many are in each of those levels. Okay, so we're starting with the 1s level. So we're going to write 1s. And how many are in the 1s level? 2 of them. So then we write a little 2 on top, a superscript. And then you jump to the next row. We're in the 2s level. How many are in the 2s level? 2. And then keep going across. Now we're in the 2p level. How many are in the 2p level? 6. So we're going to write a little 6 on top. And then 3s level. How many are there? 2. Keep going across. We're in the 3p level now. But we're stopping on silicon. So 2. It's the second one in the 3p level. 1, 2. So we're going to put a 2. So all the S's are going to have 2s and all the P's are going to have 6s until you get to wherever you're stopping. And that's the one that can change, the one at the end. Okay, skip like 2 lines and then let's do another example. We're going to go back up and fill in something here. So you want to skip some space. And we're going to do nickel. Nickel is number 28. So we're starting on the 1s at the beginning, just like we did before. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d, and we're stopping on the 8th one in the 3d level. So 3d8, 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, guys, any questions so far on those first 2 examples? I know this is like new weird stuff that you've probably never seen in science before. It's like very specific to chemistry. So. Okay, let's do a third example, skip 2 lines. Let's do lithium. Lithium is number 3 on the periodic table. So we're not going to have much to write down because the elements that are closer to the beginning of the periodic table don't have as many electrons, so their electron configuration is shorter. So we're going to start at the beginning. We have 1s2 and 2s1. We're stopping on the first one in the 2s level. Let me tell you a little trick. If you were to go back and add up all of these numbers on top, 2 plus 2 plus 6 plus 2 plus 2, it's going to equal 14. And SI is number 14 on the periodic table. So that's one way that you can go back and make sure that you did it right. You can add up those little numbers and see how many electrons there are. Okay, so like this one, if you add up all of these numbers, nickel is number 28, so you should have 28. This one, 1, 2, 3, and lithium is number 3 on the periodic table. Okay, let's do one more example. Skip 2 lines, and we'll do chlorine. All right, chlorine is number 17, so we're stopping right here. We know we're going to end up on 3p5, right? The 5th one. So everything else is going to be the same as what we've been writing, and we're just going to stop at 3p5. Now, this is great for a multiple choice test. Whenever I give you the electron configuration, just look at the end, and you know where to stop. You know what element it is. So we're going to start from the beginning. We have 1s2, 2s2, 2p6, 3s2, and we're stopping on 3p5. And if you were to add up all these, 11, 12, 13, 14, 15, 16, 17, and chlorine is number 17 on the periodic table, so it matches. Okay, so that is the electron configuration. Our title is electron configuration and orbital notation. So we're going to go back in and actually draw a representation of what the electrons would look like filling up energy levels. Okay, and that's called the orbital notation. So we talked about how many different orientations there are for each shape. Okay, and at the bottom, I'm going to write those out. We have S, P, D, and F. The S level has one orientation because it's a sphere. No matter how you orient a sphere in space, it looks the same on all sides, only one possible orientation. The P is a dumbbell. It has 3 different ways that it can be oriented around the axis in space. D has 5, and F has 7. And remember that each orientation can hold a maximum of 2 electrons. So that means that S can have 2, P can have 6, D can have 10, and F can have 14. All right, so let's go back up to number 1. Every time we see an S, we're going to draw 1 space underneath it because S's get 1 space. P's get 3 spaces, okay? So here's another S, 1 space. P, 3 spaces. S, 1 space, and P, 3 spaces. Now, I don't know if you're OCD like me, but I kind of like to draw a line in between each level so I can see what belongs to what. But you don't have to do that if you don't want to. And now we're going to go back in and we're going to draw the electrons. Now we said that electrons have to have an opposite spin because they want to stay far apart from each other. They have a half spin. So we're going to draw half of an arrow to represent a half spin. And we also talked about how electrons don't like other electrons coming in and sitting like right next to them unless there's no other space available. Okay, so keep those rules in mind as we draw these out. So in the S level, there is one space that can hold 2 electrons. And this one has 2 electrons. So we're going to draw one going up. It's a half arrow going up. And then the other one has to be spinning in the opposite direction. So we're going to draw the other electron with a half arrow pointing down. This S sublevel also has 2 electrons. So one up and one down. The P level has 6 electrons. Now watch really carefully how I fill them in. You don't want to be like that girl at the football stadium who sat right next to me, okay? So we have 1, 2, 3. They're going to spread out as much as they can at first. And then the fourth one comes in and he's like, oh, there's no room. I guess I'll sit next to you. 4, 5, and 6. So they're actually going to fill in separately and then go back in and fill in the other spots once the room gets taken up. This S level has 2, so we're going to draw one up and one down. And then the last level has 2. So there's 3 spaces with 2 electrons. So remember, they're going to space themselves out from each other. They're not going to crowd in. So you're going to have 1 and 2. And that's orbital notation. So I'm just going to abbreviate that with ON so you know which one is which. So the one on top is the electron configuration, and the orbital notation is the one with the arrows. So it doesn't have to take that long every time. I'm going to show you a shortcut. Okay, this is the way I do it whenever I'm drawing this out. Let's draw out all the spaces. We have S is 1, S 1 space, P 3 spaces, S 1 space, P 3 spaces, S 1 space, and D has 5. So I had mentioned in the lecture that when you're playing a video game, you have to pass level 1 before you get to level 2. And you have to pass level 2 before you get to level 3. So we know that up until the last level, everything else has to be filled in. Because you're not going to have electrons filling in spaces over here if these aren't full already. So what you can do is you can just kind of, except for the last section, just go back in and fill in all your arrows without thinking at this point. Okay, so let me show you. Okay, so that's kind of faster, right? Just get that out of the way. And then the one that you have to focus on is the last section. So look at the end. How many does the last section have? 5 spaces. How many arrows am I going to draw? 8, because of that 8 right there. So the last one, we just pay attention to that one. 1, 2, 3, 4, 5, right? Because they spread out first. And then they go back in 6, 7, and 8. I want you to try out number 3. It's real short, so just try it out, see if you can do it on your own, and then I'm going to come back and give you the answer. And if you finish number 3 before I start, go ahead and try to attempt number 4 as well. Okay, let's check it out. S, 1 space, S, 1 space. And then I've got 2 electrons here, 1 going up and 1 going down, and 1 electron here, just 1 going up. How'd you guys do? Okay, good. All right, last example. We've got S, 1 space, S, 1 space, P, 3 spaces, S, 1 space, and P, 3 spaces. Okay. Now what I like to do is just ignore the last section and do that later and just know everything else is going to be filled in. Okay. And then we can focus on the last section. There's 5 electrons, 5 arrows in the last 3 spaces. So they're going to fill in 1, 2, 3 first, and then come back and do 4 and 5. All right, so those are your examples. You're going to need another page for your actual work, okay? And let me show you on your modules what to look out for. So on today's module, you have the notes that we went over, the PowerPoint notes, and then you have your electron configuration periodic table. So you can use that to help you with your assignment. And then you have the examples that we just did. And if you don't like the way I teach, here's a video of another girl teaching you how to do it. So you have extra resources. You can go back and rewatch it if you need to. And then here's your assignment, okay? It's 10 elements that you're gonna write the electron configuration and the orbital notation for, just like in our notes. This is the only assignment where you're gonna have to do it by hand. The other assignments will be multiple choice and a lot easier, okay? So just make it through this one and you'll be fine. Now it has unlimited submissions. So if you do it and you make a bad grade on it, you can do it again all the way up until Saturday at 5 o'clock. And that's for my class. So up until Saturday at 5, you can resubmit and do it again for a better grade, okay? Just basically write out the 10 elements on a sheet of paper and draw out the 2 notations, okay? You have to take a picture of your work and submit it that way through the assignment. So make sure that you hit the blue submit assignment button, okay? That's the one that's going to actually send it over to my grade book. And you should see confetti on your screen after you submit it. That way you know you did it correctly. Okay. Good luck, everybody. Let me know if you have any questions.